This is the second lecture on production economics, and what we've got here is a graph of total product, where total product is a function of xi, but xj is fixed, and that's important to keep in mind here. So you can just think of it as being one input, but in fact there is more than one. We're just holding the others constant. And we find that total product curve rises slowly and then more and more rapidly until it hits this inflection curve, and then it begins to decline somewhat, and it peaks at this point here. At that point, so beyond that point, the marginal product, as shown in the diagram below it, is negative. So it's negative here. And we also draw this line here, which is essentially Q divided by this input xi, and thus it's the average product of xi, which we have on this axis in the lower diagram. So we have the average product, which looks like this, if it's plotted out, and the marginal product hits a maximum at this point of inflection here, and we have that point there. And at this point, you'll notice that the average product and the marginal product are identical, which is this point here, and we find that the marginal product is falling after the inflection point, falling so it intersects the average product curve from above. And we can identify three stages of production. The first stage occurs from 0 out to the intersection point here. Stage 2 occurs between the marginal product intersecting the average product from above to the point where marginal product turns negative. And then stage 3 is where marginal product is negative, and we'd never want to produce in that region. Now, this is a contrived example, and these stages of production are fairly well contrived, and many people don't learn this anymore, but I think it's important. For one reason, it helps you identify an extensive margin, which occurs at this point here, and an intensive margin where the marginal product turns negative. Now let's return again to Euler's theorem. Suppose that this function, as a function of inputs x1 through xn, is homogeneous of degree r. Then what it says is that if we take the marginal products of each of the inputs multiplied by the amount of the input, so the marginal product multiplied by the amount is equivalent to multiplying the output function by r. So we're going to prove that. So by definition, if we multiply each of the inputs by t, then we have that t to the power r multiplied by the original production function. So we differentiate both sides with respect to t using the chain rule, and we get these results here. Then what happens is we know that this derivative of t of x with respect to t is just x1. Here it's partial derivative of t of x of n with respect to t is just xn, and we get the same result that r minus 1 times the output is on the right hand side. So all we do now is we let this equal 1, and we get this result here, which proves Euler's theorem. For linear homogeneity functions, r is equal to 1, and thus Euler's theorem leads to this result where the sum of the marginal products times the output of the sum of the marginal products of any input multiplied by the amount of that input, when they're summed together, gives you the total output. Thus, constant returns to scale exhausts the product. If r is 0, then the sums of the marginal products times the actual inputs is equal to 0. Now, demand functions for both consumers and firms exhibit this latter property. Now let's let Q be a function of x and y, where a is a parameter, alpha is also a parameter between 0 and 1, and x and y are our inputs, and y is raised to the power 1 minus alpha. And this, of course, is the Cobb-Douglas production function, or a version of it. Then the average product of x is simply q over x, which is equal to a times the ratio of y over x to 1 minus alpha. We can find the marginal product is the partial derivative of q with respect to x, and it's equal to alpha a y over x to 1 minus alpha. So we find that the difference between the two is really this alpha here. Suppose y is fixed and x is variable. Changes in y will shift the average product of x and the marginal product of x curves, but the maximums or maxima of APX, so the average product, and of the marginal product, they remain unchanged. So even though we shift the curves around, basically the maximums of average and marginal product are unchanged. Now we also define something called output elasticity. The output elasticity is the partial of Q with respect to X multiplied by X over Q, which is equal to the marginal product of X over the average product of X, and thus the elasticity of output of X is equal to alpha, as I noted above. At the intensive margin, the marginal product of X and the average product of X are the same, so that the elasticity of output with respect to X is just basically 1, where the average product and marginal product intersect. So these two are equal. Assume that Q is equal to a function of X's and is homogeneous of degree 1. Then we can divide by xi, let's say, so that we get, we divide the output function, the production function, by xi, and we multiply it by xi at the same time to keep this equal to the original equation here. So then the average product of input I is given by Q divided by xi, and it's simply this function here because we've now divided out this xi here, so that the average product turns out to be homogeneous of degree 0. Output elasticity, so this is not to be confused, the output elasticity is given by epsilon I equals the marginal product times the inverse of the average product. This is the inverse of the average product. We want to total differentiate the production function, and we get this result here. And if we divide that by Q, we get the sum of the marginal products of I times the inverse average products of I multiplied by the derivative of xi, or the total derivative dxi over xi. We let latter derivative of xi over xi equal to dt over t without loss of generality. We do this for each of the inputs, and then we get dq over q divided by dt over t, which gives us the sum of the marginal products divided by their average product. So then the elasticity, the overall elasticity, is just simply the sum of the individual elasticities of output with respect to the various inputs. Now, the marginal rate of technical substitution we've seen before, and we denote it with MRTS. So if we take a production function, Q as a function of x1 and x2, we find that along any isoquant, along this isoquant here, that when we total differentiate and set that equal to 0, what we get is dx2 over dx1, which is the slope of the isoquant at any point, is equal to minus f1 over f2, the ratio of the marginal products of 1 over 2. And we define the marginal rate of technical substitution as the negative of the slope, so that it's equal to the ratio of the marginal products. The marginal rate of technical substitution measures the reduction in one input per unit increase in the other that is just sufficient to maintain a constant level of output. Recall fixed factor production. Here we have fixed factor production in this little diagram to the right. And let's suppose we have 4 fixed factor processes. By producing output using a combination of 2 processes, the isoquant can be represented by a line segment. For example, A and B represents using this production technology here and this production technology here, both of which give you 100 units. And anything along this stretch here, AB, is simply a combination of this process, this one, and this one. And likewise on this section here, it's a combination of this process and this process. Now, we can look at linear homogeneous production function in this case where we have x1 and x2 plotted on the horizontal and the vertical axes respectively. And we see that the slope of this line, and we'll call that line an isocline. The slope of this isocline is simply an input ratio that doesn't change along that line whenever we have a linearly homogeneous production function. If it's not linearly homogeneous, then the isocline might look like this, or it might have any kind of an odd shape. For example, it might roll along like that. And but what we have here is just a smooth one that I've drawn in for those purposes. So let's recall that we have two production functions that we've looked at. We've looked at a Cobb-Douglas written here as Q times a parameter A, x1 to the alpha, x2 to the beta, where alpha and beta are parameters that are generally chosen between 0 and 1. And we have the constant elasticity of substitution production function, which is given by this more complicated expression. And this has been introduced to you earlier, where this phi was equal to, if I recall correctly, sigma over 1 minus sigma. And we'll get back to what sigma is, but it's the elasticity of output. So let's look at these functions. Both are linearly homogeneous of degree 1. The average product and marginal product decline throughout, but approach the horizontal axes asymptotically. Thus, one does not get the familiar stages of production that we saw a bit earlier. For the CES production function of degree not equal to 1, this may result in an uneconomic region of production. And if you look at this particular configuration, this particular diagram, we see these ridge lines here and here, where the slope of an indifference curve, or pardon me, an isoquant, is vertical here at this point, and it's horizontal at this point. So you never produce in these areas outside of the ridge lines. So the only place you really produce is stage 2, much like we saw earlier. And you refer to this as the substitution region because you can substitute between x1 and x2 and stay within these ridge lines. So point A is on a ridge line and is at the intensive margin with respect to one input, and on the extensive margin with respect to the other. So point A separates stages 2 and 3 for x1. So stages 2 and 3 are separated. Here's 2, here's 3. And it separates stages 1 and 2 for x2. So in this direction, we have stage 2 here, and down below, we have stage 1. Throughout the substitution region, the marginal rate of technical substitution is declining. So we have diminishing marginal rate of technical substitution. So let's look at this a bit more detail. We have x1 and x2 on these axes. We have an isoquant here, and we've got 2 points P and R. We draw a straight line from the origin to R and to P, and along the OP line, we find that x2 over x1 is equal to the tangent of this angle theta. And along the OR line, we find that x2 over x1 is equal to this tangent of phi. Now we can also draw that in this way, where we have a substitution curve, our isoquant if you like, but it's the marginal rate of technical substitution that is plotted on the horizontal axis, and the input ratio x1 to x2 on the vertical axis. The elasticity of substitution curve is called the elasticity of substitution. All right, now let's take a look at that. Marginal rate of technical substitution is, we call that S, or we define it to be equal to S, and it's equal to minus, and we'll use instead of x1 and x2, we'll use xi on the horizontal axes and xj on the vertical axes. And we then have that the marginal rate of technical substitution S is equal to minus dxj over dxi. So the total derivative of xj with respect divided by total derivative of xi, which is equal to the ratio of marginal product of I over the marginal product of j. We're going to let y equal xj over xi, and then we define the elasticity of substitution here as dy over y divided by ds over s. So the change in this function divided by y over the change in this function divided by s. So when we do that, we get dy is equal to xi times dxj minus xj dxi over xi squared, and we get that ds is the derivative of s with respect to xi multiplied by dxi, and we have a slight error here in that these should be partial derivatives instead of full derivatives, because we have s as a function of xi and xj. Now dxj is equal to the minus of fi over fj multiplied by dxi, which is equal to minus s dxi. Now we can substitute that in so that 1 and 2 become dy equals minus sxi plus xj divided by xi squared times dxi, and ds is then this complicated formula, and again we need to have partial derivatives here, not full derivatives. And we get that minus s times the partial of s with respect to xj minus partial of x with respect to xi, all multiplied by the total derivative of xi here. So then we can figure out what ds, the partial of s with respect to xj, and the partial of s with respect to xi, and those are given by these formulas here. Notice that fj squared is at the bottom of both of these in the denominator, and that the numerators look fairly similar except for the subscripts that we have on the f's. So we substitute these results, 3 and 4, into the elasticity formula here, and I'll let you just follow that along on your own, but in the end we get this formula here for the sigma for the elasticity of substitution. The change in slope along an isoquant is given by this amount here, and therefore in the end we can write the elasticity of substitution as this amount here. Notice that sigma is inversely proportional to the change in the slope of the isoquant, since xi, xj, and s, the marginal rate of technical substitution, are all positive. And we know that the again, we need to put a partial here. Pardon me, these should be full derivatives instead of partials. It's important to recall that we have that. And sigma is non-negative if the second derivative of xj with respect to xi, so the derivative of the slope of the isoquant, is greater than 0, then sigma is non-negative, or it's greater than or equal to 0. And we can look at the two limiting values of the elasticity of substitution. One where inputs are perfectly substitutable, so that this formula here, the second derivative of xj with respect to xi, or the derivative of the slope of the isoquant with respect to xi is 0, then we have the elasticity substitution being infinite. And if it's fixed proportions production, there's no substitution among inputs, so that the value of the slope is infinity, the derivative of the slope is infinite, and then the elasticity of substitution is 0. Thank you for watching this video. There are many more videos in this 2 to 3 course series. A list of videos, the order in which they should be taken, and links to them are found under Mathematical Economics at the website indicated below.